Good afternoon and good evening, everybody. My name is Philipp Mucha. I'm a CFD application engineer with Siemens Digital Industries Software, and today we're streaming out of Boston, Massachusetts. This episode of SimCenter TV broadcast is dedicated to the application of the discrete element method, the simulation of ship-ice interactions. We will start with an introduction, thereby putting the problem into the current economic and environmental context. And we will then discuss the hydrodynamics of ship-ice interaction, which helps to clarify what requirements arise for a computational method and which simplifications in the modeling process might be involved. After studying the fundamental equations behind the DEM coupling to the finite volume-based computational fluid dynamics method as implemented in SimCenter StarCCM+, we will turn to an example of a tanker advancing through a channel of brash ice. We'll conclude this webinar with a summary of the findings. So let's turn to the status quo of ship operation in Arctic environments to begin with. The recent discoveries of large reservoirs of natural gas, but also oil, as well as the geopolitical tensions which come with this, have brought the Barents Sea and its shipping passages to a renewed attention. In the interim, global warming also changing ice conditions continuously, which is extending the window of the year during which operation on these passages is possible. This in turn can pose new tasks to ship designers to account for the modified environment of ship operation. So let's reinforce our understanding of these megatrends. What you can see on this slide here is the sea ice fraction as a scalar plot for the years of 1960 through the predictions and projections to 2040. And you're basically looking at the North Pole, Arctic Sea, and Barents Sea extendedly. What you can see here is that for the month of September, the sea ice fraction dramatically shrank. If you look at the areas that are denoted red, which make up for 80 to 100% ice. So from 1960 to 2020, you can already see that in the vicinity of, let's say, economic powerhouses on the land side, there's a lot more area that is sea-free, or where there's a sea area fraction of, say, 20 to 40%. And the predictions for 2040, consistent with the trends that we are getting from renowned institutions, are even more dire in talking from the standpoint of the ice. So there will be even less ice in the month of September. Now, to put this into perspective, usually the transit in the Barents Sea would be possible in the spring to fall months, but more so in the summer. So this is extending now with these trends into October or later months even. So all these things have to be taken into account for ship designers, because depending on the mission and the purpose of the operation, now the time window that transit is actually possible. Let's take a road that is very practical from more months to the other side of the Barents Sea. Then if you can do this during more months of the year, apparently you have to take this into account in the ship design process. Now, if we look at a zoom-in view of the Barents Sea, there's mainly 4 ship passages that are in place. On the right-hand side here, indicated by the blue, yellow, orange, and red line. The reference this data is derived from is given here at the bottom. And this report also came up with a study of the safe speed in ice. So you can see here that for a sea ice concentration, for the example of a tanker, if there's no ice, it would go about 18 knots. And then as the ice concentration increases, this speed dramatically decreases to account for the additional resistance, but also structural safety concerns. Let's look at the physics of ship operation in ice, and I want to break this down to the problem of forward motion, which concerns resistance and in turn minimum power estimation. So a practical engineering approach would be to assume that the total resistance acting upon the ship hull in ice would be made of the open water contribution that would be present at this forward speed plus the resistance in ice. So the interest is also for us CFD engineers, assuming that we are all very familiar with how to get the open water contribution, how is the resistance in ice made up of? So generally, another simple model based on engineering assumptions would be to assume that the resistance in ice is made up of contribution coming from the actual braking, from the rotating, submerging, and sliding of the ice flow. So if we look at the braking, then we can manifest that the crushing of ice edge into the small pieces upon the initial contact has a characteristic shape of these that you see here. And this can be explained by failure mechanics, basically. So upon reaching of the Benjamin failure stress, ice sheet breaks up into cracks, these symmetrical cracks. I have to take a little break and remind everybody to mute themselves because I'm getting a lot of noise. Unfortunately, I don't have control over this, but it's interfering with the presentation. So if everybody could stay muted, that would be very much appreciated. Thank you. So the formation of these cusps will depend on both ship speed, but also the shape of the bow. Now, once the initial intact ice sheet has been broken and can no longer be considered intact, there is a component to the ship resistance that we can refer to as the rotating component. So here the advancing ship forces the ice floes to rotate as they are being displaced. So that refers to inertial forces associated with the ice flow motion. And the challenge here is that the knowledge of actual ice properties is not very trivial. So salinity plays a role, but also if there has been any snow on the actual ice floes, that all affects the inertial properties and therefore the forces that are associated with the resistance on the ship. Then, after the braking and rotating phase, one can say that the broken ice is displaced laterally and vertically, and the submersion of consecutive flows draws water in the opposite direction of flow motion. So the flow field ambient to the hull is changed by the dynamics of these flows. And last but not least, the ice flows that are sliding downstream and driven by the ship forward speed result in friction forces as they physically interact in contact with the hull. So if we look at what we want to discuss today, it's basically looking at the managed ice and brush ice condition. So what is managed ice? Pretty much derived from the actual name. So if you imagine that a dedicated icebreaker would break the way through for a following ship, basically taking all the load of the resistance components that we've discussed in the previous slides, and then a following ship would basically face all the other components except for the ice-breaking resistance. So this is one example of what we want to discuss today. And on the other hand, we have a situation as on the right-hand side of this slide, which is called brush ice. So here, an icebreaker also cleared the way for following ships, but there was some time between this event and the passage of the ship that we're seeing now, which allowed the ice to refroze and some of these fragments to basically form the state of ice that you are seeing in this video. So today we will be talking about these scenarios. Now, how do we, as a naval architect who is familiar with running resistance tests with StarCCM+, how do we account for this additional physical problem? So StarCCM+ comes with the discrete element method, which is a numerical method to simulate the collective behavior of a large number of particles interacting with each other and or fluid flow in the boundaries. And this model is based on the Lagrangian multiphase model as a meter-level model, if you recall the physics continua tree that we have in StarCCM+. So DEM has its origins in rock dynamics and granular flows, but what is commonly referred to as a prerequisite or good condition to apply DEM is the particle load is high, or if the particle shape is important and collision dynamics are important. Applications are found across a wide range of industries, oil and gas, mining, pharmaceutical, or agriculture. Especially the coupling between DEM and CFD recently has drawn a lot of attention in the multi-physics simulation context, and it's also now finding its way into naval architecture for the example of ship-ice interaction, but also if you want to study interaction of ships with muddy or flow that is populated with sand particles in harbor approach channels, for example. Now, let's take a look at the underlying equations, because it's important for our actual practical verification study. Because we will run a few sensitivity studies to give practical recommendations and tips and tricks on how to simplify this problem in general. So if we look at the Navier-Stokes equations on the top of this slide for incompressible flow, and think about how we can couple these to the Lagrangian flow model and what we would have to do with the Lagrangian flow problem itself, the first step to clarify is if we want to run a two-way coupling or a one-way coupling simulation. So in two-way coupling mode, the flow will drive the particles, and the flow will be updated based on the particle impact. So both dynamics affect each other, and that should only be activated if there's a physical reason to do that. And we'll get to this later for the example here. In turn, one-way coupling will be based on driving the particles, but it will be unaffected by what the particles are actually, the motions the particles are actually exhibiting. And in certain situations, this can be an expedient and viable assumption that can save a lot of computational time. So, one-way coupling versus two-way coupling. Now, if we look at the particle dynamics in general, the model behind that is basically based on Newtonian mechanics, and what we'll focus on in the next slide will be basically the contact dynamics. So you can see already here on the two equations on the bottom of the slide that it should appear very familiar to what we learned about Newtonian mechanics. So we have inertial terms, we have pressure gradient terms, and we have drag terms, and then at the very right hand side of this equation we have the sum of our contact forces, which should be the focus of our discussion here in the remainder. So let's look at how this is being modeled. So you can see here an overview of the particle equations of motions, and I want to draw your attention to the right-hand side graphic, which basically shows that the contact force between two particles, these are these two rectangles in the schematic, is basically made of a normal force and a tangential force. You can see for the normal force, this is basically as one option, a simple linear spring model, so there's a spring and a damper element. And then for the tangential force, you can see as an option, there's a spring damper model, which is in series with a slider. And the same applies basically for the rotational modes of motion. There are nonlinear contact models available in StarCCM+ as well, but today we'll confine ourselves to the linear spring model. So this was relevant for the contact forces. If we look at the coupling degree now between water and air and ice, Then we'll eventually have to revisit the conservation equations regarding mass and momentum. And what is important to consider here is that the displacement of the continuous phase by the dispersed phase is accounted for by way of the volume fraction. On the left-hand side, you can see how a volume fraction for a combined Eulerian and Lagrangian framework would be defined. And in the end, the volume fraction of all Lagrangian phases for which the two-way coupling is active will be accumulated, and this volume is seen as a void by the continuous phase, in our case by water and air. And the volume available for the continuous phase decreases by just this volume fraction. So in the end, if we have this information, we can account for mass, momentum, and if required, energy transfer, and this will be balanced by the two equations which we see here. I want to remind everybody to hit the mute button at this point in case getting increasing noise. Thank you. So these are the, roughly speaking, the mathematical equations that are behind this of DEM and CFD. So let's turn to our practical test case. So today we're going to apply this method to the motion of a very large crude carrier, which here is the Japan Bull carrier as a publicly available test case, dancing through brash ice. The main particulars of the tankers are here shown in the left-hand side table, so 280 meters in length, 45 meters in width, and so forth, and we will be running this in full scale. So the side view of this geometry, you can see the cross-section of the ice channel. So basically our solution domain will consist of a block that is representative and a finite anticipation of our ocean. And then there will be two ice sheets that at the defined thickness constrain the flow laterally across this thickness. In between and underneath, you can see that the ice particles represented by DM particles and star CCM plus are conglomerated. And on the very bottom of the series of schematics here, you can see a schematic from the textbook, basically of how brash ice is defined. And usually, if you have the intact ice sheets to the port side and starboard side, you can see that there are these characteristic humps to the negative vertical side here that form if the brash ice is basically formed. And you can see here, upon initializing the ice flow basically in star CCM plus, that this situation can very well be resembled. The table on the left-hand bottom side gives an insight into the baseline values that we'll define for a static friction coefficient between ice particles. So this is taken from the literature, and as I pointed out, this is a big challenge in modeling this with the computational methods in general, because it's a very complex physical circumstance, and to come up with one coefficient that accounts for the contact dynamics between these particles is actually a non-trivial task. But we are dealing here with values that are used in the literature, and they are basically also or can be used as free variables in any type of calibration effort, or if you have in-house experience and knowledge about these material properties, that Plus offers, you basically specify them at your desire. What is more important for the resistance and contact forces is the static friction coefficient between ice and steel. And here we'll be looking at a range from 0.1 to 0.6, and that represents the very, very pragmatically relevant range of what you can find in the literature and what you can find between different ice conditions. So anything below would be unconventional, and everything above I would venture out to say also. So let's dive into our verification study. So first we'll be looking at the general simulation problem, because there's a few things that we have to sort out before we can actually confidently say we know what we're doing. So traditionally, what I call the upstream injector approach is being used for such problems. So this means that you'll use the conventional setup for a ship resistance test. So you have one domain, which is static, and the ship is stationary, and the flow will be specified at some point upstream. The injector line for the DM particles will be defined someplace between the actual inlet of the domain and the ship. And the particles will be injected with the velocity of the flow. The advantage is here denoted or marked in the green color font. We will economize on the control volume count because we have a small domain and a single domain. And more modeling is required for the longitudinal motion of the ship because we switch the reference frames and the flow is initialized at the negative forward speed. The drawback of this approach is, technically speaking, this is an inconsistent reference frame because upon injection of the ice particles at some point between the bow and the inlet of the domain, the ice particles are already free to interact with each other and transport and exchange momentum. So upon meeting the ship, this is not the consistent reference frame, and this becomes clear if you look at the general Eulerian and Lagrangian problem from a textbook point of view. The question is, how important is that? We know that is a simplification, but how important is that, and when does it become a problem? The second approach that we'll be taking is what I call the moving ship approach. So here we will constitute a much bigger domain, and the ship will move through the flow and ice fields at rest. So the overset mesh method is required to accomplish that, and the particles will be injected beforehand. So we have an ice field that already covers a decent area, and the ice and water will be at rest, and the ship will move through it. So the advantages are apparent. It's a consistence in terms of the reference frames. Ice and water are at rest. There's no particle contact and motion prior to exposure to the ship-induced flow or geometry. The disadvantage is there's an increased modeling effort, which involves also the overset method. So we also buy in more interpolation errors, and this all comes at a higher computational cost because, first of all, the overset problem introduces an overhead, but also the fact that we'll inject this vast field of ice beforehand is more expensive than the injector line approach, very trivially speaking. And a couple of other numerical issues that can arise from it, handling the motion, etc. So let's take a look at just how this injector line approach would work. So everything at rest, the white space you see to the left and the right represents the ice sheets. The ice is going with the flow around the ship. If you look at this front view, you can see the ice coming in from the injector line and impacting the hull. So this is what we'll look at first. Now, the question is, how do I constitute a brash ice field that resembles somewhat realistic conditions? So in StarCCM Plus, you will have a lot of latitude in terms of coming up with the distribution function for the particle size and other properties relevant for DEM. We'll here resort to the community CDF of Rose and Remmler, which also stems from basically rock dynamics and granular flows, which is very suitable to model the conditions that we'll encounter for brash ice. You can see here on the left-hand side what happens if you modify the coefficient B, let's say between 0.5 and 1,2. So with one condition, and that's just a representative sample, with one condition, you will resemble a distribution where you have a lot of particles with the minimum size of the range you specify between 0.5 and 2 meters. And with the other distribution, you have a more uniform distribution in terms of the amount of particles at a certain diameter between 0.5 and, let's say, 0.1 to 5 meters. So generally speaking, you have a lot more larger or medium-sized particles than smaller particles. And the cumulative distribution functions that go with it are depicted here on the left-hand side. You can see on the right-hand side also what the general baseline shape is that we are using to constitute this brash ice field. So it's basically two cubes, one of them being duplicated and rotated at 45 degrees in two directions, and then you'll get a shape that looks like this. So this can be an arbitrary shape, so you could come up with more disc-like shapes, triangular or polyhedral shapes, whatever suits the needs. The range of the particles, as I said, for this full-scale situation, vessel 280 meters long, is 0.5 to 2 meters. So before we dive into the plots and numbers and figures, this is basically the comparison between the brash ice field in StarCCM Plus, top perspective view and a view from the propeller or at the propeller, and then left-hand side on the bottom, you can see what we try to resemble. Now, first thing is let's do the due diligence and get a feeling for what the discretization sensitivity is for the grid that we use. The grid that's being used doesn't differ too much from what you would be using for an open water condition, except for that we have these ice sheets to the right and to the left, and have to assign appropriate boundary conditions to their walls. But just to get a feeling for the remainder of this presentation, on the left-hand side here you see the time history of a resistance for the upstream injector approach. So at 8 knots, for this 280 meters long tanker, will be coming in with roughly 320 kilonewtons for the total resistance, here seen with the black curve, and the combined contact and resistance from air and water is the blue curve, and the red curve here you can see is what the contribution will be from the contact with the ice. So if you run a discretization sensitivity study, which here in that sense means the coarse grid has been refined by factor square root of 2 twice to constitute the medium and fine grid, and the time step at each of these refinement steps is refined as well, because this is consistent with keeping the CFN number constant. Actually, it can be shown that if you only refine in one dimension, you can arrive at basically an invalid discretization study that will not give you the opportunity to extrapolate based on, for example, Richardson interpolation. Here's just a side comment for everybody who wonders why a time step was refined at the same time. Now, if you look at the total resistance, we can see here that the difference is rather small in the resistance values, and we can see that we do not have monotonic convergence, but that's in the very last digit between the coarse and the medium mesh, and there's a lot of things that attribute to it, so we shouldn't be too concerned here. What's more important is looking at, for our problem, because we're very familiar with deep water resistance tests and their discretization errors, is looking at the contact forces. So there's a few things that drive the change of contact forces in terms of discretization. The first thing is we changed the entire flow field, so that means every change in the flow field that is attributed to discretization change will also affect the response of particles. So even in a one-way coupling setting. In a two-way coupling setting, it might be more severe even. But also, let's not forget that if we globally define the entire mesh, we will also change the discretization of the hull surface. So in the end, the contact forces will be constituted by the contact surface that the particles and the ship hull constitute. So if you have a finer discretization on the hull, that means that you will change the contact surface between a given particle size and the hull. So, but here you can see that apparently our initial discretization of the hull was fairly accurate in terms of the shape, and the changes in contact resistance were negligible between all these three discretization levels. So in the remainder, we will work with a medium grid to economize on computational cost. Now let's look at a bird view of the ice field with this upstream injector approach. So you can see here a rather uniform distribution of ice particles as they make their way across the length of the hull. What can be said here basically is that their dynamics pretty much follow our intuition of fluid dynamics. So as they encounter a reduced cross-section, which would be starting at the foreshoulder of the tanker, they will conglomerate more, and there will be a higher packing density because the cross-section of the flow is lower. And then as they go downstream past the aft shoulder, this will relax a little bit, and they will somewhat build or constitute the wake that we see here. Now, let's look at the material properties. This is very important because I think this is the property that's most relevant for the design process. So, left-hand side plot, we look at basically recalling what the time series looks like, getting a feeling for what is the contribution of the contact force compared to the force that comes from the fluid and water, and what is the total force. So the left-hand side shows what we found out before if we use a friction coefficient between ice and steel of 0.6, and the right-hand side shows that what happens if we change this to 0.1. So you can see here that a 6-fold increase leads to a 3-fold increase in the contact force. So this will be a very, very important parameter, given the simplicity of the model, to calibrate your DEM-CFD coupling model for if you have experimental data. Or if you know very well the ice properties and can set the friction coefficient accordingly, you will have a way better chance to be spot on with any experimental value. So this is very important because the difference between these two contact force responses is enormous. So if we look at another driving factor, that would be packing density. So recalling the cumulative distribution functions and the two scenarios we came up with, one with parameter B of 0.5 and one with parameter B of 1.2, we can see that, not surprisingly, if we come up with an ice field that has a lot more particles of the medium to higher size range, we will have much more dense brash ice fields, and in turn the contact forces will increase. So the sensitivity to packing density is very strong. The more larger particles are present, the higher the contact forces will be. So knowledge about the cumulative distribution functions that are suitable to resemble a model test or a scenario that is known will be very crucial next to the ice-steel friction coefficient. Now let's look at the degree of coupling, and let's first look at global forces, so integrated values. So here we see resistance tests at 4, 6, and 8 knots. On the left-hand side, it's total resistance. On the right-hand side is the contact forces. So left-hand side, we have 3 data points, or categories of data points: one-way coupling, two-way coupling, and no ice. So not surprisingly, no ice and one-way coupling, they will be, that's for the right-hand side, they will be on top of each other. But if we look at the general trends, we can see that there's not a big difference that would basically warrant to use the more sophisticated two-way coupling. For this speed regime, for these sizes of ice clumps, and just the width of the channel, basically. So on the right-hand side, you can see the contact forces. Of course, there the third data point with no ice is taken out. You can see the differences are also negligible. So the sensitivity to the CFD-DM coupling degree is very weak for the present load case. However, the higher the particle load, because here we use the medium constellation, and larger particle sizes, the higher will be the impact of running two-way coupling. And this becomes even more evident and is reinforced by the following two slides. So, if we look at the left-hand side here, what you see is the waterline on the port side of the ship. We'll take the flow as symmetric, roughly, so it will be the same on the other side. So we can see that while the integrated values, the forces and contact forces integrated over the ship's, or the pressure and contact forces added, pressure integrated contact forces added over the ship hull were very much insensitive to the degree of coupling. We can see that local flow phenomena are indeed responding to whether we run one-way coupling or two-way coupling. On the right-hand side, you can see the velocity fields normalized by the ship forward speed across the width of the channel. So the other schematic here shows where the cross-section is, and what we're plotting is from the side of the hull, on the port side, to where the ice sheet sits, we're plotting the weight, basically. So we're looking at the local longitudinal velocity and normalize it by ship forward speed. And you can see that there are distinct differences locally between one-way and two-way coupling. So the anticipation is that if we use a higher particle load and larger ice flows, that will increase the importance of the rotating and submerging resistance that we discussed initially, and in turn it will drive us to the requirement of running two-way coupling, which the CCHS comes with. Now let's look at the sensitivity of the reference frame. So recall I introduced the upstream injector approach and the moving ship approach. You can see here the contact forces differ considerably. And let's look at why this is for this load case. So the only thing that will give some sort of evidence why we see such an increase in the contact forces is to look at the local flow fields. So there's two scalar plots here. The one on the top is from the upstream injector approach, the one on the bottom from the moving ship approach. What we see here are the particles in their physical shape, but they are basically assigned colors of a scalar plot of a quantity that I want to call the normalized disturbance velocity. So what is meant by the normalized disturbance velocity is, keep in mind, we have a different approach in the method. So in the first method, the upstream injector, the ship is stationary, the flow is introduced at the ship forward speed and not in negative direction. And then the particles themselves, they will take a characteristic velocity. So if you combine that and normalize that by the actual ship speed, that is an indicator for how much the particles are disrupted by the presence of the ship. So that means for the moving ship situation, we can basically come up with a common denominator for the comparison to study how much of the particle will be disrupted and accelerated, or how they will behave in their dynamics as the ship is plowing through the field of ice. And you can see here that for the moving ship approach, where the reference frames are consistent, there is a much higher disruption of particles, especially across the midship body. And you can also see that the weight behind the stern is somewhat more irregular than what you can see in the upstream injector approach, and that is attributable to the fact that if you inject at the velocity of the flow, there is a more dominant downstream drift of these particles. So they are less prone actually to exchange momentum in a lateral side or also vertical side, which for very large particles and high particle load density, this would not be quite realistic. So this is basically evidence that if you meet the criteria that you have high particle count, large particles, then to be on the safe side, you should use the overset mesh method, the initial ice field in the channel, and have the ship plow through it in the consistent reference frames. Now, let's take a look at some more metrics, because we saw the integral forces, we saw a local flow field study, but let's pull some more metrics. One of them is basically looking at the number of particles present at each of the sections that are displayed here on the right-hand side schematic. So, not surprisingly, ahead of the ship, the particle number is fairly similar. And then you can see as we approach the midship area, which is the most important one for the contact forces, you can see that in the overset or the moving ship method, there is a substantially higher particle count, which is attributable to the higher disturbance velocity. The particles were disrupted by the presence of the ship a lot more than in the upstream injector approach, because the downstream drift is more dominant. And then you can see it evens out a little bit towards the stern, that the important part in terms of integrating the pressures and summing up the contact forces is in the large midship section, which you can see here across the board for one-way coupling overset, the particle count was higher. And this can also be shown if we actually look at what the contact forces are here in the scalar plot. So for using the same scale for the upstream injector approach, it's barely visible, the magnitude of the contact forces, while we have a clear line of contact for the moving ship. This is for the same scale. So it just indicates that the magnitudes are substantially different. Now, of course, all this comes at a computational cost. So if we look at this resistance test, if we don't have any ice, then this will be in blue here, which is the lowest solver time per simulated second. Then we'll add some overhead because we are invoking DEM if we use one way. Now if we use two way, we add a substantial overhead, but the disclaimer here is that there were not any optimization techniques, so to say, employed here in terms of the load balancing and the DEM time step. We were using the default values for the DEM method, so there is room to bring this cost down. But quantitatively, keeping the same values, you can see that this comes a little down as you go to the one-way again, but using overset. This will, of course, be more than with the one-way upstream injector approach. And then the most expensive would be to run two-way coupling and the moving ship approach. Now, another thing that is of interest here and how this computational framework can be leveraged is, for the designer, what is the impact on the propeller? So if I have my minimum power estimation in check, I will be concerned about the loads on my propeller, because possibly ice can hit the propeller. So the first step was to introduce to the bare hull resistance case a virtual disk as a body force propeller, and propel the moving ship case with this virtual disk. And then a disk was formed with the diameter of the propeller in the propeller plane, which records all the crossings of any type of DEM particles over time. Left-hand side, you can see all the crossings across the steady-state conditions. And on the right-hand side, you can see representative of the time step of, or the time instance of 90 seconds, what it looked like. So on the starboard side, seen from the stern, you can see there were 3 DM particles that interfered with this plane. So a total of 300 particle crossings were recorded, which is an indicative evidence. We have to bear in mind that the virtual disk is also a simplification for propeller-ice interaction. So this is very helpful because now I know I have 300 crossings in this passage, so I may check if they would actually interfere with the blades, because it will behave different than the virtual disk. So let's just look at an animation of the overall process for the next few seconds before we look at the amendment of this case with the propeller. So this is the Brash ice field around the JBC in motion. This is how the contact forces look. And then for this moving ship method, the propeller was added. Ship is fully appended, so rudder could be moved. And then the presence of the propeller, next to how the hull disrupts the flow of, or the interaction with the ice, you can see the propeller also has an effect. So, bearing in mind the indicative evidence of the crossing of DM particles through the propeller plane, the next step was, from the simulation that you saw in the previous slide, to check where and if actually DM particles or ice particles have hit the propeller. So you can see here for a given series of an X curve from a rotation, you can see here the pressure side and the suction side of the propeller, and you can see that this propeller turning in the clockwise direction, we do have contact forces, and they are also of high magnitude because the contact forces are not compared to the contact forces on the hull, which is important for the propeller design, because not only are we looking at the longitudinal direction here in terms of the structure-ice interaction, but due to the shape of the propeller blades, we also have to account with getting the magnitude for lateral and vertical magnitudes of the contact force. So that is a high value, 321 kilonewtons. So you can see here pressure side and suction side, they both see contact. So now we could, if we wanted to, add a solid stress model in StarCCM Plus and compute the structural responses of the propeller blades, and that could tell us if, for the given ice field, we would have to make changes to the design or if we are in safe operation. So, concluding remarks, a general computational framework for the simulation of ships advancing through brash ice based on coupled CFD-DEM was presented. Special attention was paid to the computation of contact forces, so the sensitivity of friction coefficients was shown to be consistent and strong. The sensitivity of packing distance was shown to be consistent and strong. The sensitivity to the degree of CFD-DEM coupling was weak, but it's depending on the load case. Higher packing density, larger particles, the more likely you have to run two-way coupling. The sensitivity to the reference frame of motion was shown to be consistent and strong, but it's also load case dependent. Future developments on our side are focused on the modeling of breaking of impact ice sheets based on particle bond and failure models. So there's failure models. I'm getting some feedback again, so I'd like to invite you to mute yourself so that we can proceed in the final minutes. So there's a simple failure model and a constant rate damage failure model implemented. But it is really an extension of the work that is presented, as we're looking at intact ice sheets. And other future applications are focused on maneuvering, so taking that from the straightforward motion to horizontal plane motions, and then fluid structure interactions, for example, for the propeller blade deformation. Validation of the presented method by way of comparison of the simulation to experimental data is also required for a final assessment and the reliability of the presented simulation framework. And if you, for example, engage platforms like ResearchGate, you can already find a lot of research papers in the field that successfully validated this method. So this concludes our talk. I thank you very much for your attention, and we'll have time, of course, to address your questions. Please enter the questions through the chat window. I will read them out loud, and basically then also provide my response out loud to the group. Thank you very much. Looking forward to your questions. The floor is yours.
Có thể có số phân định chỉ định đó